Hey guys, today's video is going to focus on Lewis structures for covalent compounds and also ions. So just as a quick reminder, when we talk about covalent compounds, we're talking about compounds that exist between nonmetals, where there is a sharing of electrons between two elements that have pretty similar electronegativity values, right? So again, we have a sharing as opposed to, say, an electron transfer resulting in charged ions. In any case, as far as Lewis structures go, these things show in two-dimensional how valence electrons are arranged in a molecule. So again, it just keys in on the valence electrons that are actually engaged in chemical bonding. They only show us connectivity of the atoms. Okay, they tell us nothing about the molecule's 3D geometry or shape. In the coming days, we will get to VSEPR, valence shell electron pair repulsion theory, that will allow us to talk about things like trigonoplanar, tetrahedral, octahedral, things of this nature. Okay. Before we get into the rules of Lewis structure, just a couple quick reminders that I think you'll probably fall back on in a number of different scenarios. And when we go to draw Lewis structures, one of the first things to consider is that we really are always looking out for atoms to have 8 electrons around them, right? We refer to this as the octet rule, okay? That being said, there are some things to kind of take note of. First and foremost, hydrogen only ever wants to have 2 electrons. We refer to this as the duet rule. And given that it only wants to have 2 electrons, it's always going to be on the outside of a molecule or an ion, okay? Likewise, halogens are also going to find their way on the outside of a molecule because they only ever make one bond. They have 7 valence electrons. They merely need an 8th in order to have that full octet. Okay, so both hydrogen and halogens, we're looking for those to never be central atoms. Towards satisfying the octet rule, we're looking for atoms to only ever have 4 bonds. Okay, so central atoms can only ever have 4 bonds, or 8 electrons, given that a bond is composed of 2 electrons, unless that atom is in period 3 or lower. Okay, we will see some examples where we have what's called expanded octets, where actually we're able to violate and get up towards 10 or 12 electrons around some central atoms. Okay, and not quite yet, but also, as with most things, there are a number of exceptions. Okay, both boron and beryllium can achieve stability without having a full valence shell, without satisfying that octet rule. So more on that to come. So just a quick kind of refresh concerning the rules in terms of how to construct Lewis structures. Okay, now these rules are simply guidelines. How you choose to construct them is kind of up to you. We probably did something a little bit different in honors last year or the previous year, but nonetheless, the first thing we're going to want to do is count the total number of valence electrons for all atoms within that compound or molecule. Okay, in the event we have ions. For negative ions, we're going to be looking to add the same number of electrons as the charge. For positive ions, we're going to be looking to subtract the same number of electrons as the charge. From there, we look to construct a skeleton structure. Okay. More often than not, the central atom is typically going to be the first atom written in a formula, or perhaps the one that is fewest in atom number. Okay, we're going to see an example in a little bit where it's a little tough to decipher, and we actually look at the Lewis structure for the individual atom to help make an informed decision. Once we go ahead and construct kind of bonds between the central atom and all the peripheral atoms towards that skeleton structure, from there we're going to count the number of valence electrons that are still available. Knowing the number of electrons that are still available, then determining the number of electrons that are still needed, we can compare the two. As we compare the two, if the number of electrons available are equal to the number of electrons needed, it's really easy. All we do is start to add a whole bunch of lone pairs. Okay. In the event these numbers are not equal, right? If perhaps we have less electrons available than what's needed, this is when we look to add bonds. Okay, and as we add bonds, say double, triple, or perhaps even multiple double or triple bonds, we will be looking to reduce lone pairs of electrons, given that we share a little bit more efficiently. Now, if the number of electrons available supersedes or exceeds rather the number of electrons needed, then we're talking about these expanded octets, where that central atom could have upwards of 10, 12 electrons. Okay. Quick little reminder just to check that Lewis structure at the end to make sure either the duet rule is satisfied, the octet rule is satisfied, or that the exceptions, if we have something peculiar that we can draw upon our exception memory and make sure things look good there. Okay, let's jump right in then. We are going to start straight away with I don't know, pretty straightforward example, I guess. We're going to start by talking about nitrogen trifluoride. Okay, so the first thing I've done is I've looked to determine the total number of valence electrons. And just as a reminder, when we talk about valence electrons, we talk about the electrons contained in the outermost energy level, or where N is the highest. And so for nitrogen, N's the highest as far as the second energy level goes. And so this is where we see we have 5 valence electrons. For fluorine, again, N, where it is highest, is the second energy level. And here we see there are 7 valence electrons. The number of valence electrons coincides with the column number or the group number. Those two things are synonymous on the periodic table. Okay, with just a quick reminder that helium has 2 valence electrons. So here I've labeled the periodic table with the first column and second column. So 1 valence electron and 2 valence electrons respectively. We skip the transition metals and we jump over to the column that has boron in it, 3, 4, 5, 6, 7, 8 across. But again, this exception here where helium, because it only has 2 electrons, only has 2 valence electrons in that 1s level. I've highlighted nitrogen and fluorine, and per what we've just evaluated in terms of its electron configuration, we find that nitrogen does indeed have 5 valence electrons and fluorine has 7. So column number yields the same number of valence electrons. So let's get to it. So I have my 5 valence electrons for nitrogen. I have 7 valence electrons for fluorine, but there are 3 of them. So in total, we have 26 electrons we get to play with, okay? When I go to start my skeleton structure, I stick nitrogen in the middle. I construct bonds with some peripheral fluorines. From there, I've identified that I've used 6 electrons. Well, if I've used 6 electrons and I have 26 available, that means that I still have 20 electrons available, okay? That being said, in order to fill a octet, or full valence shell for the remaining atoms, I'm going to need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So the number needed, so 20 electrons needed, is equivalent to the number of electrons available. And so I'm in great shape. Like, if I evaluate this between a single shared pair of electrons and between 3 lone pairs of electrons, that fluorine has 8 electrons surrounding it, thereby satisfying the octet rule. Likewise for this fluorine, likewise for this fluorine. It's coming a little cramped, but this centralized nitrogen here also has 8 electrons surrounding it. 2 in a lone pair and another 6 in 3 shared, or what we call bonding pairs, okay? When we go to reconstruct this, I don't want to see this as your final answer. I want to see something like this. We are going to get in the habit of representing electron pairs, whether bonding or lone pairs, as lines. Okay, this gets rid of kind of the ambiguity of making all these dots. Do you have 6 dots around an atom? Do we have 5? Like if we write really lightly, is that an electron right there, or is that just kind of a mark on the page? So let's get in the habit of using lines to represent 2 electrons, okay? So this is our completed Lewis structure for nitrogen trifluoride. We move on to something that's perhaps a little bit more complex, okay? HCN, okay, so hydrocyanic acid. Now here, I'm looking at this and maybe first things first, I'm just counting up the number of valence electrons. So 1, 4, 5, I'm looking at 10 electrons total, okay? And in trying to figure out what the central atom is going to be, the very first element written in that formula is hydrogen. So per the rules that I've given you, maybe we think it's hydrogen. But hydrogen's only ever going to form 1 bond, right? Here's the Lewis structure for the hydrogen atom. And as we see, it's really just, needing 1 more electron to have a full valence shell. When I do the same for carbon and nitrogen, I find that carbon, traditionally is going to form 4 bonds. And this nitrogen, because of the way that it already has, this this kind of pair of electrons has 5 valence as opposed to the 4 in carbon, nitrogen's pretty much only ever going to have 3 bonds. So with that in mind, I'm of kind of a suspicion that carbon is going to be our central atom. It has the capacity to form more bonds. Carbon very often is a central atom within molecules, okay? So at this point, when I go to construct my skeleton, I have carbon in the middle, hydrogen over here, nitrogen over here. Now, hydrogen's already done, right? By having these 2 electrons tied up in that, again, shared or bonding pair, the duet rule has been satisfied for hydrogen. Carbon and nitrogen still got some work to do. I've used 4 electrons, okay? 2, 4. I have 10 electrons available, which is to say I only have 6 electrons available at this point. Well, in order to have a octet around these things, I need 2, 4, 6, 8, 10. I need 10 more electrons. So 10 electrons needed. Because I need more electrons than are available, I know I'm going to have to start making double bonds, perhaps even triple bonds, okay? Every single time, you need to lower your electron count by 2. What that means is that you're going to create another bond. So 2 electrons, let's say to reduce by 2 electrons, we're going to create a bond. And as we do this, okay, so as we look to construct, say, a bond between the carbon and the nitrogen, by adding in 2 electrons, we can essentially remove a lone pair from each one of those atoms that the bond is made between. And so by adding in 2 electrons, we remove 4, thereby having a net reduction of 2 electrons. Okay? That being said, we've still used 2, 4, 6, 8, 10, 12 electrons, and I'm only allowed to use 10. So I need to generate yet another bond. So in fact, we find that hydrocyanic acid actually has a triple bond between the carbon and the nitrogen. The final structure that I'd like you guys to kind of roll with is HC triple bonded to the nitrogen with that lone pair outside the nitrogen there. Again, in final pictures, looking to construct lone pairs as lines. Okay, that wraps up the structure there for HCN. We move on, we talk about ions. Okay, ions are really no different than what we've seen in these previous 2 structures. The one thing to think about is, besides just tallying the total number of valence electrons, we're going to have to add in this case 2 additional electrons. So carbon has 4, oxygen has 6, however there are 3 of the oxygens. So in total, we have 22 electrons. Remembering to add back in 2 electrons that the carbonate, that CO3, is picked up from some outside source, we're looking at 24 available electrons. I stick carbon in the middle. I go to construct my skeleton structure. At this point, I've used 2, 4, 6 electrons, which means I have 18 electrons available. To satisfy the octet for all atoms involved, I need 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. So I need 20 electrons. So again, what I need exceeds what is actually available. So because it's only 2 electrons that I need to kind of reduce, I merely need to construct 1 more bond. So I'll choose to make a double bond between the carbon and this oxygen. I will eliminate this lone pair. I'll eliminate this lone pair. And the oxygen you choose is kind of arbitrary. This gets into a concept called resonance that we will get into more later this week. Towards constructing my final answer, I'm going to stick this whole thing in brackets. I have lone pairs around the oxygen. I got the centralized carbon, another peripheral oxygen, and then this is, as written right now, kind of asymmetric. I'll extend that bracket down a little bit. Oh, sorry guys. Okay. And then outside of the brackets, I'll indicate the charge. So whenever we have an ion, we're going to use brackets. We're also going to stick the charge as a superscript off to the right-hand side there. Okay. Again, you notice the absence of a lone pair on carbon. Its octet is satisfied because it has 1, 2, 3, 4 pairs of electrons, all of which are shared or bonding pairs. single bond, and what we see there is a double bond, okay? Last thing we're going to talk about is this concept of expanded octets, okay? There's a handful of elements, and these are pretty popular, that have this ability as a central atom to kind of violate the octet rule. In fact, atoms of elements in and beyond the third period of the periodic table have the capacity to have more than 8 electrons surround it. The reason behind this is because the d orbital, which hasn't really been fully utilized at this point, so say like a 3d, can accommodate these extra electrons and ultimately be used in bonding. We will get into this over the coming days as far as hybridization goes. So for this example, for phosphorus pentafluoride, phosphorus has 5 valence electrons. The fluorine here has 7, but there are 5 atoms. So in total, I have 40 electrons I get to play with. Now straight away, I see that there are going to be 5 peripheral atoms, right? As soon as I put a phosphorus in the middle and I start to draw a whole bunch of fluorines around this thing, like already I'm in violation of the octet rule. Already that phosphorus has 10 electrons surrounding it, okay? But again, it has those d orbitals, the 3 d orbitals in this case, that haven't really been occupied yet by electrons, and they can accommodate these extra electrons. So at this point I've used 10. I'm allowed to use 40, okay? So that's 30 electrons still available. So let me go ahead and kind of satisfy the octet for all those peripheral fluorine atoms there. I'm making, or I'm adding, I should say, 6 electrons around each of the 5 fluorines, which is to say I needed 30 electrons in total. These two are equivalent, so this is my final structure there for phosphorus pentachloride, okay? When you're looking at rule 5 here, this third part, if electrons available are greater than electrons needed, then we'll distribute extra valence electrons to the central atom, okay? We didn't need that here. We didn't have any extra, but had we had, say, 32 available electrons, right? Had this been 32 available electrons and we only needed 30 to satisfy the octets on those peripheral fluorines, then we would have actually added another lone pair to the phosphorus, okay? So if we violate that expanded octet, those extra electrons will go on the centralized atom there, okay? The last thing I want to discuss is what we refer to as valence band theory, or this idea of potential energy diagrams in taking a look at things like bond length, okay? So, these Lewis structures are great at depicting what's going on with valence electrons and how bonds are generated and the difference between shared and lone pairs. However, they don't really talk about why chemical bonds exist. And for this, we need to revert back to quantum mechanics, okay? Valence band theory, okay, A theory, one of several we're going to use this year, assumes that electrons in a molecular orbital, okay, that electrons in a molecule occupy atomic orbitals of the individual atoms. So when we say atomic orbitals, we're talking about S, P, D, and F. This is in contrast to what we'll see in a few days, talking about hybridized orbitals, and we will touch upon the concept of molecular orbital theory, okay? But for now, we're going to focus strictly on valence band theory. So what we're going to do is we're going to take a look at the formation of an H2 molecule from 2 hydrogen atoms, okay? Just keeping in mind that this covalent bond, okay, nonpolar covalent bond, is formed by the overlap of 2 s orbitals. So again, here's what a hydrogen atom looks like. Here's what another hydrogen atom looks like. What we are going to take a look at is the process of if this is a 1s orbital from one hydrogen and this is another s orbital from another hydrogen, how is it that these 2 atomic orbitals, these 2 s orbitals, these 2 hydrogen atoms come together to form a molecule, come together to form a bond, okay? So what we have here is a potential energy diagram. We'll just kind of break this down. In this first scenario here, what we find is that these 2 hydrogen atoms and kind of the representative s orbitals here are so far apart that they don't really interact, Okay, so we assign this a potential energy of 0 kJ per mole. Okay, as these two atomic orbitals, these s orbitals, and subsequently the hydrogen atoms come closer together, the electrons of one atom are going to be attracted to the nucleus, the positively charged nucleus of the other atom. Okay, so while there's going to be some electron-electron repulsion, right, between the two separate atoms, and there's also going to be some nuclei repulsion, right? The protons of one nucleus are certainly going to be repelled by the protons in the neighboring nucleus. We find that the source of attraction of electrons from one atom to the protons in the other atom's nucleus, that's starting to kind of overcome that repulsive force. And we actually find that there is a decrease in potential energy, an increase in magnitude, but overall decreasing. And this kind of goes along with this idea of spontaneity. When we talk about energy, when we have this exothermic process, bond formation, this is going to be a favorable thing. Down here, where we have the lowest potential energy, this is where these two s atomic orbitals are, there is substantial overlapping. This is where we find that these are going to be the most stable. The potential energy decreases. Again, the magnitude is increasing, but the value is technically decreasing, okay? Again, we have the substantial overlap, and this is representing the perfect distance where all repulsive forces are minimized, right? But all attractive forces are maximized. This leads us to the concept of bond length. Okay? When we talk about bond length, this is literally just the distance between two atoms or ions. We'll get into ionic compounds in our next unit, where the energy is minimal, where there is the greatest kind of decrease in potential energy. We say that the shorter the bond length, the stronger the bond, and therefore the harder it is to break the bond. And this is what we refer to, and this got cut off a little bit, as having a higher bond energy, okay? The stronger a bond is, it requires more energy to break that bond. Thanks, guys.